are there, but I usually don't in the series circuit because there's only one current, so I don't have to specify the current. I got to specify the voltage because there's three, right? There's VR, there's the voltage across the radio, which is 9 volts, and what's the other voltage?
Voltage, the whole
VT.
thing.
So I got to subscript the voltage, but I don't have to subscript the current because there's only one. So I don't subscript that. But I want to make sure you understand how to get this power right here. And this is the power dissipation of what? The resistor. So I want to take the 3 volts times 200 milliamps to get 600 what? Power is greater than watts. And since I kept this in milliamps,
It should be milliwatts.
it's going to be milliwatts. So basically 0.6 watts. So what does that mean to you as a designer? That means when you build this circuit, you go to Radio Shack and you buy the resistor, you can get a resistor no smaller than 0.6. If you get it smaller than 0.6, you hook it up, it will drop 3 volts for a couple seconds, and then guess what? It burns up. You can't get rid of the heat fast enough. So you can't make this too big, but you can make it too small. So really you want to probably double or triple this. You can get it 10 watts would work. You'll never have to worry about it burning up. You can make it too small, but not too big. So when you're doing textbook problems, you know, you can just calculate the voltage drop. But if you were actually going to build this in lab, or you were designing this for somebody, you have to take into consideration the power. Okay? You got to take that into consideration. Some of you guys hook up stereo systems and you hook up other things in your cars. You got to take into account power when you do that. You just don't hook wires up and make it work. You got to do some calculation. It's called engineering. Well, before you taught, that's what you do. I used to hook up stuff and it would work and they'd drive off, but who knows what was really going on? Mathematics. You want things to work properly. So power dissipation is important. On the quiz, it'll be a separate problem. I'm going to ask you to design a circuit like this, reduce voltage with a resistor, and in the second part, I'm going to ask you to figure out the power dissipation. You got to remember to use the voltage drop of the resistor and the current through the resistor. It's going to be exactly like this problem. And I say that because I know that maybe not half, but people are still going to miss it. Even though I'm telling you, I'm going to do exactly the same thing. People are going to miss it. Don't know why, but it happens every year. Question?
Could you give us another example problem of that then? Just so we can.
Yeah, all night. Sure. Want to do another one? Before we do the other problem, what if I want to put a fuse in there? How would I do that?
Place it before you would have to place it before the resistor, and then you would have to have it equal to your power going into it. So
Okay, yeah, that's right. But theoretically, do I have to place it before the resistor?
No, you put it at the end so the power.
I can put it where?
Anywhere.
Anywhere I want, because I understand that. What do I understand? What blows a fuse?
Too much current.
Current. And what do I know about the current?
That's the same.
It's the same. You see, what's your name? Alan asked, well, how do I know which rule to apply? What I'm giving you is little pieces of a puzzle. Little simple things. Like, all these ideas are simple. But then you're able to put them together and it gets complicated. But if you keep the simple, the basics, just kind of keep that in mind, then these are little tools you can use to solve problems. So I understand I can put the fuse anywhere in here. And so I go in here and I buy, let's say I put the fuse right here. And by the way, this is a fuse. That's an AC source. These are two different things. So I'm going to put my fuse right here. Now, do I want to go to the fuse that's 200 milliamps? Is that what I want?
No.
Why don't I want 200 milliamps? Who in here thinks the current is going to stay exactly 200 milliamps?
Not going to be. You're going to lose a little bit when because that the fuse is like it's still like a resistance. I think.
The fuse itself is like a resistance? The current's related to temperature. Did you know resistance changes with temperature? Sometimes the temperature go up. I mean, a gnat or a fly could go by and pass gas on this, and it's just enough to blow the fuse. So you want some safety factor there. So you might want to, you know, that's called I worst case. I worst case. You might make it whatever you want. You might make it 15% above the load current, right? So I might make it 15% or 20% above the load current. So I don't know. You can decide that. It's just whatever safety factor you want. But I wouldn't put a 200 milliamp fuse in there. Maybe 250 or something like that. Okay, so we'll do more of this stuff later on. I'm just pointing something out to you. But let's do another problem, and then I think that's going to be enough for tonight. Because what I like to have is the people who in lab to have a little break. You might want to, you know, get something. I got two questions. I think yours was first. And then
Question I have, in placing the fuse in that circuit, if your power is flowing this way and you want to protect your radio, why would you place it anywhere in the circuit after the radio?
that's a very good
That's
question.
what I was gonna ask too.
Okay, now, to answer that question, you got to understand what's doing the blowing of the fuse. It's not the electrical current.
Oh.
Okay. Now, this may surprise some of you. Okay, so let's say I'm in Cincinnati, right? I'm in Cincinnati, and my girlfriend's in California. That's about 4,000 miles away. So I pick up the telephone, now not a cell phone. I'm talking about like old-fashioned landline. That means when I pick up my phone, and she picks up her phone, there's a physical connection between her phone and mine all the way to California. There's current flowing from my phone to hers, 4,000 miles away. When I pick up my phone and talking to it, the electrons that leave my phone don't get to California instantaneously. Matter of fact, it will take many, many, many hours because they bump into all that resistance. They're traveling really slow. They have a certain drift velocity that you can even calculate. But yet, the instant I pick up my phone, she hears my voice, right? Almost instantaneously. Why is it she can hear my voice? What traveled from Cincinnati to California at nearly the speed of light? The sound. The electric what?
Current.
Force. The electric field. Remember when we talked about
Electricity.
let's say I have these two charges, right? If I take this charge and move this over here, I take it and move it over. Let's say these are free to move. If I take this and move it over, what happens to this one? It's going to feel that push instantaneously. Well, really not instantaneously, but that push travels at the speed of light. It travels at the speed of light. So that force travels through what we call the electric field. It works the same way with magnets. You feel it instantaneously. So the current over here that leaves my telephone may take a long time to get to California, but she can hear me right away because that electron right by her phone, by her ear, feels the force instantaneously because it's traveling at the speed of light. We see that fuse works the same way. Even though the actual electron that leaves this to blow that fuse, even though it has to travel all the way around, that electric field, the electric field is the same everywhere here. And the minute that electric field goes up because of the current, it's going to blow that fuse no matter where it is in that circuit. So it's not the electricity that travels at the speed of light, it's the electric field, the electric force that travels at the speed of light. Did we talk about electric field in here at all?
Yeah.
Or not?
Yeah.
A little bit.
Because as you see, it's the engineering, we go really into that, and then here I want to mention it so you guys know it, but I don't know who I told what, I really don't. Does that make sense to you or not?
So you're saying it happens so fast that the damage isn't going to occur?
That's exactly right.
Okay.
It happens instantaneously. The speed of light, for all practical purposes, is instantaneous. You can't go fast. That's the limit to speed. You can't go faster than that. If you could go faster, this is crazy as it sounds. This is a good question for him. If you move so fast that you can move to the speed of light, you'll go so fast you start to slow down. Now you really got to smoke a lot of weed to understand that, but that's what the physics teaches us. That's what it is.
You can be anywhere at any time.
There is no time.
That's what I mean. You can
At the
be
speed of
anywhere.
light, at the speed of light, what happens to time? It stops. It stands still. This is all theory, but this is what it is.
Theory of relativity, 101.
Yeah, really. So that is. So what's your name? Nathan is exactly right. if you think in terms of just kind of things moving around, it seems like, well, I want to put that right, I want that to vote first, but really it doesn't matter. Because that electric field travels so fast, it's instantaneous. You can, by convention in America, we put it on the red wire. If you hook up radios, you know what I'm talking about. But you can put it on the black wire, it's still going to blow. Okay? That's a good question. Let's do one more problem as practice, and then we'll call it a night, and then the people that's got to laugh. Did I answer? Did I skip you?
No, I actually had the same question as him
Oh,
about that.
okay.
About that there.
I'm on the smart people group.
Okay, I'm not either, so let's do this one. I do want to see you guys have a smart people fight.
Oh my god.
I almost saw one.
I'm just jotting shit down.
Are we doing the next?
Up here.
We're gonna do
Yeah, once you get the better score.
question.
Oh, I can understand.
Normally, you say that you have 12 volts that come into the source, and we need 9 volts for the radio.
Yes.
And you say that we have to put the resistance that's going to reduce the voltage. We suppose that we don't have 3 volts left.
We're gonna drop 3 volts.
Yeah. Do you think that, I think that before, when the current goes, lead the resistance, we're going to have 9 volts. We're going to have 9 volts after that.
Right here.
Yeah.
9 volts.
9 volts. But the radio also have the resistance, right?
Yeah, the radio
radio
does have
also has
resistance.
Have also the resistance. That means, I suppose that we trying to estimate that that's going to be 9 volts, but it's not always 9 volts. That can be 8.9 something.
No, if
What
you're
is?
gonna,
Okay.
he's asking, since the radio has resistance, it's not gonna see 9 volts, but it will be, but anything after the radio won't see 9 volts, since the resistor only affects in a series circuit what's after it.
Yeah, I got it. Yeah.
Does that make sense?
Yeah.
Now, another way to look at it, you brought up something really good. Here's what you could do if you wanted to. You could say, all right, I have a 15 ohm resistor, and I got this radio, right? I got this radio connected to 12 volts. But you said that the radio has a resistance too. Can anybody tell me how to calculate the resistance of the radio? What would you do?
Test it from side to side.
I messed with the law, and I got 45 ohms. I did like 10 lines of
When you know the
So-
voltage drop
If you know the
across
voltage-
it, and then you just do the exact same thing what we just did over here.
If you understand what he just said, you know what's going on. If you don't, you really need to study this. You do exactly what we did here.
Yeah.
If you know the voltage drop across the device, you know the current through the device, what do you know?
You
The
know,
resistance of the device. So the resistance of the radio is going to be the voltage of the radio divided by the current through the radio. But the current through the radio, since this is a series
2.1
circuit,
million.
there's only one. So how do I
200
calculate it?
million.
What's the voltage drop across the radio?
9 volts, right?
What's the current through the radio?
0.2 amps.
So what is the value of that?
45.
See, I got back doing 10 lines of RT equals R1 plus R2.
So what you can do
You
if
did
you
the
wanted
wrong way.
I
is
did, yeah. I
put
did
45 on, you can forget that there's a radio. Now you know that I got 3 volts across there, and I got what?
9 volts.
9 volts across there. Does it obey Kirchhoff's voltage law? Well, the sum of the voltage drops got to add up to what?
That's the total.
What about the current? Is the total current really equal to the total voltage divided by the total resistance? Let's see. The total voltage is how much?
12 volts.
12 volts. What's the total resistance?
60.
50 plus 45 is
60 ohms.
60 ohms.
Somebody take a calculator and divide 12 by 60. Then what do you get?
Open to.
20 milliamps.
So yeah.
So really what we do is we model things as resistors. I just drew the box there so you can visualize a radio. But you can abstract from that and model it as a resistor. It all works out the same. I think in answer to, I don't want to point and I can't say your name, so you got to help me. I need some initials, I need something, because I can't say, what's your name again?
Landry.
What's my name?
Your name? I know Singletons.
See, so it's Shingleton, but you guys see how he said that?
Shingleton.
So he can't say, and I can't say your name, because it's just, so we're cool, so we,
Yeah.
You can say John, is better.
I can say John,
Yeah.
okay, and you can say Ron. You say Ron?
One.
Okay. Now, this is cool. How could you, do you speak French?
Yeah.
How do you say, what I like about, I told you this, French, you
You
can
say
say,
anything and it sounds.
and it sounds sexy, right?
Yeah.
So I want you to say in French, class is over. Listen to this. Class is over. How do you say that in French?
Is la classe est finie.
Okay.
Oh, wow.
I'm gonna give you a practice problem to do, and then when you come back, is that okay? That we'll do it when you come back. We'll do it.
Practice.
We'll do it as a practice problem, and then what I'll do. This won't be on the next quiz, so you don't have to worry about it. We'll do some more design stuff. I'll just give you a sheet because we're running out of time.
Since we don't have class next time, and we're, I guess, way back on our quizzes, the next quiz that we do take in 2 weeks, will that be chapter 4 through?
It's gonna be the next topic.
Just
topic
topic sheet 2.
Just topic.
Yeah.
Okay.
I don't like putting a lot of stuff. I want to run it behind so you guys have a chance to let this stuff sink in. So was it you that, who asked for the practice problem? Is that okay if I do that? If I will do one and I'll give you a sheet of it. This is some really neat stuff and this is good to do. But yeah, if you have your homework, I'll take it. If you have lab, let's take like a 10-minute break and we can get in the lab early and get out early. Is that cool?
Yeah. Sign in?
Okay, and
And the homework, you want me to just, I have another book though, if you wanted to like, give me other work out of the other book, I don't know.
no, you can, you want to take my book and bring it back and get your book?
Yeah, I mean, that's fine with me, he said he's gonna